So let's get started with lab 10 demo. The aim of the lab was to design a FIFO block, right? So that would receive all the packets from the previous block in the NetFPGA pipeline, and then allow the processor to do any functionality or processing that has to be done, and then send all those packets to the next block in the NetFPGA pipeline. Our initial design was, we started with the small FIFO that was given to us. We built upon that and the drop FIFO that was already available in the NetFPGA reference router kit. But that kind of didn't work out. So although behaviorally we could get it up and running, that had a lot of issues while when we actually put it up on the NetFPGA, right? So we discarded that idea, and we came with another design. So what we did was we basically came up with a state machine, the FIFO that actually has a data element and a state machine built around it, right? So this is a snippet showing the working of the state diagram. Apologies for its bad quality. So it has 4 states. The first is idle. So upon reset, our state machine is in idle state. There basically it waits for the packets to come in, right? So the packets, so that's why in underscore ready is asserted here. That means it's ready, right, for the packets to come in. Now the moment it receives the packets from the above block here, it latches onto the first packet that is there, and in the next clock cycle it goes to the receiving stage, right? So in the reception stage, there the control bit is the ready bit is still high, so it keeps on receiving the data. But towards the end of the packet, the moment it sees the control bit being non-zero, that indicates the last the last word of the packet. It then asserts the ready to 0, right? So that says, it'll just receive one packet and then it'll stop receiving. So that is there. And then also it latches all the packets, whatever the packets that you have received, or all that data is being latched, and then it goes to the next stage. So here is the execution stage. So in the execution, it's basically we have a flag called processor enable and processor disable. So processor enable will be asserted initially. That indicates the processor that is there. So that'll tell the processor to start begin to start its operation basically. So that is there. So processor underscore enable is asserted, and after the processor is done with whatever it has to do with the data that it has gathered, the packet basically, it asserts this processor underscore disabled flag, right? So in the next clock cycle, it'll jump to the transmission stage. So in the transmission stage, again we take so whatever the packets that have been done, so that's post process, right? So the processing, everything is done. So it'll start transmitting those packets to the next block in the NetFPGA pipeline, right? So that is there. And we have used the same data element. So as you can see, this FIFO block will contain a data element, and the FSM is built around that, the state machine, right? So that data block that is there, that will also act as a data cache for the processor. So we are using the same data block. So all these packets are coming in from the previous block, so that is being stored in that data block there, a block RAM basically. And then in the execution stage, the processor uses the same data block as if it's a data cache, right? And then the transmission the transmission stage, the same cache or the same data memory element that is there, that will be used to send the data to the next block. So that is how it works. And one thing to note about the processor underscore disabled and in underscore ready here. So in these two states, we have to pay some attention. So first thing is that when we actually start receiving the last word, so that is when we have to deassert the in ready, right? So that is when we have to make in underscore ready 0. That is to say that don't send me the data in the next clock cycle, not in the same, but in the next clock cycle. So that is done. For those purposes, I've latched the data. I'll explain when talking about the Verilog code and how it's what hardware is synthesized there, right? And another thing about is processor underscore disabled. So we have a special instruction in the processor that indicates that after all the instructions, we have a special instruction that indicates that it's done. So that's an exit condition. That is the one that makes that p underscore di, processor underscore disable, as 1. So that is again a register, so a flip flop basically. But then what happens is, in the next clock cycle, so that will stay high for one clock cycle, right? In the next clock cycle, it should be reset to 0. So that functionality is also implemented, right? Okay, so let's look at the Verilog code for that, how it looks. Right, so this is the finite state machine. So the interfaces are basically clock, reset. I'll explain about the packet count a little later. So basic clock and resets, and these are the interfaces for the net FPGA modules, right? So all the all these signals which have in as their predecessor, so those are for the previous block, right? And then this is for the next block, so all these interfaces. And then since the processor is using the same data memory element that is there as its data cache, so these are its interfaces, right? These two are for basically enabling and disabling the processor, and these are debugging. So if you want to query any data element, you can give the address and you will get the data whatever that's stored in that element, right? That is there. So I have the same the state machine that was demonstrated here. The same the Verilog code has been written to synthesize the hardware for that. I have used separate combinatorial and sequential blocks just to keep the code more readable. We can also do it in the same block, same always block, but I just wrote it such that the code is readable, right? So whatever transitions has to happen in one particular stage, so I've written that using case statements, right? So for every stage that keeps on repeating, and after that the transitions, the sequential transitions that has to happen, that has been written in a separate sequential block with a case statement for each state what has to be done, right? So that is that. So that is how the finite state machine is synthesized, right? And the pipeline is the simple same pipeline that we used in the last lab, right? A simple 5-stage pipeline that is there. So we have used the same, except that the data cache has been commented out. So we are not using this anymore. Instead, so for the EXMEM stage registers, whatever the output that has to be got, so that is from input, that you get from the FIFO itself. So hence these interfaces, right? So that interface has also been declared here. So these interfaces are for that, and processor underscore disable is the output, right? So that's the usual thing. So the pipeline is based on our RV64i that will get executed, but we have added one extra instruction. So just a random thing. I have made sure that this instruction's opcode and the function fields does not match with any of our previous instructions, function 3 field and opcode, so that we don't have conflicts. I have added that in the added that in the control unit. So whenever the control unit encounters that instruction, right? So whenever this opcode, the control unit encounters this, so it sets that PIDI field to high, right? So we're not doing with anything with PIDI flag right away. What we want, the functionality we want, is that at the end, right? So after the processor is done executing for any operations for that particular packet, we want it to go back to again PC0, right? So we have to start executing the same set of commands again for another packet, right? So we have also made this like a branch and an exit condition, right? So it'll branch and it'll exit. So, and the branch target address has also been hard coded for that, right? So it'll just jump to PC0. So that is there in branch unit. So this is the thing, right? This is our usual thing, right? So whenever we encounter a normal branch equal instruction, this is what we'll do. So the branch target address in that case will be PC plus our immediate value. But look at what happens when this flag is high. The processor underscore disable flag is high. from the control unit. So when that is high, the branch target address is directly 0 and the branch taken is always true. So that is the changes we have done, right? So that is there in that. Those are the only changes for the processor we have done, and our usual finite state machine is there. So these two have been integrated here in the master. So basically I've instantiated both the FSM and the pipeline, right? So and all the memory interfaces here, the inputs here for the memory interfaces will be the output from this block, whereas the outputs here will be the inputs for this block, right? For example, address, the memory address. So the memory address is actually the output from pipeline, so it wants to query that address, so it's the input for this block, right? Same thing with data in, data out, write enable, and the actual enable of memory block. So how do we stall the pipeline, right? So that is one important question we need to ask. So whenever you're in idle stage or transmitting stage or reception stage, you want the entire pipeline to be stalled. So that's why we make use of this enable flag here, right? So at all the states, the processor underscore enable flag is 0, right? Except here, in all the states, it's in the processor underscore enable is 0. So that is given as input to our pipeline, actually pipeline's enable signal. So that time it will be stalled, so the PC won't increment and our entire pipeline will be stalled. So the PC won't increment because only if we have given an enable here also, right? So that is there. So all of those instantiations has been done, and we have also given two outputs. This is just PC underscore out and processor disable. That is the one we use to disable, right? The PC underscore out is just for debugging, to make sure to just show that the PC is actually incrementing and our processor is working, right? So basically we can add any once the this design is working, we can add any functionality in that. We can get control at the packets level, right, at the bits level, right? So we can modify the contents of the packet. We can change its IP address. We can change its content. We can do whatever we want, right? Because we have complete access to the packet here. So that is left to the user what they want to do. But we just want to keep the code simple here. That's why we initialize the memory with two basic instructions, and then they're not going to do a lot. They just add instructions to the register files themselves. They're not going to do any functionality, but this is at the end, it should branch, right? So it should set the processor disable flag high, and it should go back to the PC 0, right? So that was the intent. Although the functionality, we have not decided on what functionality should be implemented. The user is free to do that. You can basically write any code, and also the right pointer and the depth of the FIFO is visible, right? So you can see the right pointer. You can see the right pointer here. Just a second. So just a second. Yeah, the right pointer and read pointer that I have declared here, that will be visible to the pipeline block, right? So that is there, and there is also a depth field, the count, right? So that is there. So the count is the depth field. So how many words of that packet have you received, right? So if we have those two variables, basically you can go anywhere, play around with the packets, the words of the packet, and do any kind of operations with that. Those two, we can take it inside the register file of the pipeline itself, and then essentially the user becomes invincible, right? So you can do any functionality. So that kind of serves the purpose of a network processor. So yeah, that is the design. And in the master.v, we have instantiated everything, and the interfaces are defined equally, right? So let's look at the behavioral simulation of that. So what I've sent is so you can see the data here. So whenever the in underscore write is valid, that is when the data is there actually. So in these two fields, so the control bits of the first word and the last word of the packet will be non-zero, right? I've just set it to 1, right? So this the control bit being non-zero and the in underscore write being non-zero indicates that is the start of the packet, right? And the control bits for the entire body of the packet will be 0. This again, it depends on the design you're designing this for. we are using the same reference router kit pipeline design. So that is why this is how the data format is, right? So it has only one module header. So that is why the control bit will be non-zero for only for one, the first this thing and the last word of the net FPGA. So this is the first word, this is the first word, and this is the last word. As you can see here, this is very interesting. So in the clock cycle, so this is the last word, right? So this is when you're receiving the last word. So right when you see that the control bit is non-zero in the reception state, you should set the in ready 0. That is because if the in ready is still high here, the previous module that is there, so the previous module output port lookup module is there, that will start sending the next packet itself from the next clock. But we don't want that to happen. We just want to take one packet and start processing it, right? So that is why we should, it's kind of like, see, looking back in time, right? So if you have to receive a packet here, you have to assert the ready bit here. But if you don't want to receive packet in this cycle, you want to set the in ready 0 in this cycle, in the previous cycle itself. So that is what is happening. That is achieved. So basically in ready is made a combinational logic. So whenever we see that the the control bit is non-zero in the transmission reception stage, in ready will be deasserted. So that in ready will be sampled in the next clock cycle, and the output so the output port lookup, that is the previous block, thinks that okay, this person doesn't want to receive the data anymore, and it won't send that. That ensures successful reception of only one packet at a time, right? So that is happening. So I've sent one packet here and another packet here, right? So we ran the simulation, right? You can look at the processor disable flag. So initially the state will be in idle here, and then it'll go to the reception, and then it'll come to the execution stage here. So at the execution stage, you can see that the PC is getting incremented, right? So it was 0, 1, 2, 3, 4, 5, 6, and then again it comes back to 0, and then it gets stuck at 1, right? That means the processor has been disabled successfully. So corresponding to that, processor underscore disable is also asserted high, right? So that whatever the instruction we had written here, we had designed it for, right? So that is the exit condition, that is working, right? So it is asserting the processor underscore disable high. At the same time, it is also branching to the very first instruction, right? So that is happening, right? And whatever the data you had sent here, so let me zoom in that. So this is the data 1 1, and then 0 2 0 3 0 4, and then it goes for 1 7. So let's look at out control and out data. So after, you can see that it's in execution stage. After the execution stage, see the PC stuck here, right? After the next clock cycle of processor underscore disable being set high, you can see that we are getting the output at the output block, the whatever the next block is, that is getting the output. So out underscore ready is high here. That means so that's basically an input to the FSM. I've just set it high. That means the next block is always ready to receive the data. So even if it is not ready, so for example out ready becomes 0 here, then even then our design works. So it will basically pause, and then again it will start sending the data, right? So that is also working. So out underscore write is high here. So from this you're getting 1 1 0 2 0 3 0 4, basically whatever the data we have sent, so that we are receiving. Right after the last packet, the outright becomes 0, right? So that is happening. So that was for the first packet sent here, first packet received here, right? So the second packet is sent here, the same second packet is received here. Again, you can see the PC underscore out is incrementing here, and after that the processor underscore disable is high, and then it goes back to the PC1, right? So that functionality is done. And then if you look at the write pointer and read pointer, even they are working. So the write pointer is incrementing here after we had after we receive the first packet, right? That means this is latched, and then this is latched, and so on, right? See, the write pointer is incrementing while the read pointer is not. So that is incrementing, right? Now the write pointer is 7, that means it's pointing to a blank location, right? So where the next location it should be written to, right? and then when the next packet comes, again the right pointer is incrementing, and then after it is done, it stops at the next location you have to write it to. Same thing with read pointer. Read pointer increments only when you are when only when you want to send the data to the next block, right? So you can see here, so you are getting the data here and the read pointer is incrementing only in that area, right? So same thing, second packet you are getting here and the read pointer is incrementing only at that region, right? So one functionality we implemented was, so as I told you, basically the user becomes ubiquitous here. I mean, he becomes super powerful here since he's got complete control of the network packets and he can do a whole lot of things. What we did was a very simple thing. We just incremented the count, right? So we had something called packet underscore count variable. So whenever you receive the packet, every time you receive a packet, just increments the count, right? So see, when we receive the first packet, the count is incremented, right? And then when we receive the second packet, again the count becomes 2. It's 0, first will be 0. When you receive the first packet, it will be 1. And when you receive the second packet, it will be 2, right? So that's the packet underscore count. So that's a simple thing. And then we integrated that in master.v, and then that was integrated into the netfpga pipeline, the ids.v, the netfpga user data part.v pipeline, right? And then we basically gave the hardware, we gave the interface through our PC using packet underscore count, PC out, and even mem address query and mem data out. So these two are basically for debugging purposes, right? And this is basically to show that our pipeline is working, and also PC out we have given so that to show that the PC count is actually incrementing, right? So that is there. Now my teammate is going to demonstrate the functionality of this in netfpga. We generated a bit file using this, and we tested it on the netfpga and it is working perfectly. Only overhead it is adding in terms of around microseconds, right? So it's not adding too much of overhead onto the bandwidth, the processing. Basically, if the bandwidth is around if you're getting a throughput of around 900 mbps, with this you'll get around 899 or 898 mbps. So that is, I feel, very minimal and almost at line rate.
Hello guys, welcome to the NetFPGA implementation of Lab 10. So basically, let us try to load the bit file and check the ping. And we have actually interfaced the count to a hardware register. So we can count the number of packets which will move through the router which we have created. So basically now I'll just load the bit file. So we can see that the bit file is successfully loaded. So next we'll have to start RKD. So I'll do that. So now RKD is started. So first, after starting RKD, let us try to see the number of count of packets. There are approximately 49 packets. Now we'll try to ping our node N0. So when we ping, the ping is working, and we'll send 4 packets. After we send 4 packets, we'll check the count. So it is 85. So this ping will create a network traffic of almost 8 packets. So we can see that 73, and now before running the ping it is 73. After running the ping it is 85. So totally there is a difference of 8 packets. So we can confirm that our design is working. Thank you so much, guys.